examples using the quadratic formula. So the quadratic formula can be used at any time to solve a quadratic equation. And the reason for that is because the quadratic formula is derived from completing the square on a standard form equation. And we've discussed that completing the square is always a valid solution method. So therefore, a quadratic formula should be as well. So when you're faced with a quadratic equation that you need to solve, when in doubt, you can always use this method. So off to the side here, I have the steps that we need to follow in order to solve a quadratic equation using the quadratic formula. And then off to the right, I have an example that we'll do as a side-by-side to follow this step-by-step process. So step one, set the equation equal to 0. And it's also worthy of noting that when we use the quadratic formula, our equation needs to be in standard form. So let's make a side note of that. So one thing can always use, and then the second thing, equation needs to be in standard form. And as a reminder to what standard form is, ax squared plus bx plus c. Once we have the equation set equal to 0, then we can properly identify a, b, and c. If it's not set equal to 0, then you're going to misidentify them. So in this case, drawing parallels to the standard form, we can see that a is 1, b is equal to 10, and c is equal to 2. Now, once we've done that, we can substitute those values into their respective locations in the quadratic formula. The quadratic formula, as a reminder, is negative b plus or minus b squared minus 4ac all over 2a. When we make the substitution, I suggest you put the values in parentheses to avoid arithmetic error. The next step says to simplify the multiplication and addition within the formula. So we just want to clean this up. So it's negative 10 plus or minus, and I want to take care of the arithmetic underneath the square root. The thing to keep in mind, if we want to do this off to the side, is performing the correct order of operations. So the first thing I would do is square the 10. So think PEMDAS, order of operations. I take care of these exponents and I get 100. And then it's minus, and this whole quantity here is a result of multiplication. I have to do multiplication before I do addition subtraction. So I'm going to do minus, and I'm going to carry out 4 times 1 times 2, which is 8. Then I can perform the subtraction and get 92. So what I do not want to do and what I want to avoid is doing 100 minus 4 and then multiplying it by 1 and 2. So what's underneath here is 92. On the bottom, 2 times 1 is 2. So I've taken care of all the multiplication and addition within the formula. Now we have to simplify the radical. So we're going to look at the square root of 92. When simplifying a radical, my first suggestion is to determine, is 92 a perfect square? Because if it is, it makes our life easy. In this case, it's not. So there's 2 ways you can simplify the radical. One's with the prime factorization tree. The other's identifying the largest perfect square that goes into 92. But I'll do the factor tree for this example. So 2 and 46, 2 and 23. I've reached all prime numbers. If you prefer, you can cross out the numbers that have been broken down to avoid confusion. Group, I have a pair of 2s. 23 cannot be grouped with anything. For all my pairings, I remove that number once per pairing from outside the radical. So there's one group of 2, so I remove 1, 2. Anything that didn't get paired goes back underneath. So 9 square root of 92 is the same thing as 2 square root of 23. So I substitute that in for square root of 92. Then the last step says reduce equation by dividing by GCF. So I look at all the numbers that are not within the square root. So I don't want to consider what's in the square root. Can they all be divided by the same thing? The answer is yes. So I'm reducing the equation by a GCF of 2. I divide them all by 2, and here's my final answer. So let's look at some other examples to hammer home how we use the quadratic formula. In this example, we want to solve this quadratic equation. We're going to use quadratic formula. First step, set it equal to 0. This will allow us to properly identify A, B, and C. A is 1, B is 7, and C is 10. If we tried to identify A, B, and C from the initial equation that was presented, we're going to misidentify B and C by calling them negative 7 and negative 10, and therefore that will throw off our answer. So once we've identified A, B, and C, substitute into the equation. So we would substitute A, B, and C into their respective locations in the quadratic formula. Let's clean up the arithmetic. 7 squared is 49 minus 4 times 1 times 10 is 40 over 2. So this will equal negative 7 plus or minus the square root of 9 over 2. Once we've done that, we simplify the radical. The square root of 9. We'll notice that 9 is a perfect square, so this whole thing equals 3. So that made our life easy. If I check to see if it's a perfect square, I don't have to do that full breakdown. Negative 7 plus or minus, instead of square root of 9, I'm now going to write 3 over 2. Now this answer doesn't have a radical in it, but that's okay. We just have to know how to interpret that plus minus. That plus minus means we have plus 3, and we have minus 3. And we simplify both of these. Negative 7 plus 3 divided by 2 will get us negative 2 and negative 5. And here are the two solutions to the quadratic equation using the quadratic formula. Next example. Already set equal to 0. A is 3, B is negative 4, and C is negative 1. Negative of a negative. Substitute A, B, and C. Negative of a negative gets you a positive. Negative 4 squared is 16 minus 4 times 3 times negative 1 is negative 12 over 6. Minus a minus gets you a positive, so we're going to have plus 28 in there. Simplify the radical off to the side. Broken down into all prime factors, I'm going to pair up any repeated prime factors. Any groupings, I pull that number out once per group. What I didn't group goes back underneath. There's the simplified version. I'm now going to replace square root of 28 with 2 root 7. Final step, see if we can simplify the equation by dividing by a GCF. So the numbers I'm considering are 4, 2, and 6. They're all divisible by 2, so let's do divide by 2. And there's our final answer. Already set equal to 0. Identify A, B, and C. This example will present a new scenario that we need to know how to handle. A little bit different from the previous examples. Substitute in, so negative of B plus or minus b squared minus 4 times a times c over 2 times a. Clean up the arithmetic, so it becomes a positive 1 plus or minus. Negative 1 squared is positive 1. Minus 4 times 2 is 16 over 4. Get x equals 1 plus or minus the square root of negative 15 over 4. So this is the first time we've seen a negative under the square root. So when we go to simplify this, the issue with the negative under the square root is a square root is asking you what number, when multiplied by itself, gets you this value that's underneath the square root. So when I think of real numbers, are there two numbers that when I multiply together, in the event that they're the same, will result in a negative value? And the answer is there are no real numbers where that would happen. Because if the number was positive, multiplying it by itself will give you a positive number. If it was negative, multiplying it by itself would also get you a positive. So to handle this, we have to introduce a new set of numbers, which are called the imaginary numbers. And that number is I, and it equals the square root of -1. I is the value that when you square it, gets you a negative value of 1. So the reason we introduced that is because now I can write -15 in the following way: -1 times 15. And then radical properties allow me to split this. And then when I identify square root of -1, that is I. So that's the additional step when I have a negative under the square root. Essentially, the shortcut is you just erase the negative and put an I out in front. Once you've done that, you proceed as you normally would. We look at square root of 15. Can we simplify that? 3 and 5, there are no pairings. So what's not paired goes back underneath. And I get what I started with. So this also brings up the point that when there are no groupings to be had, remember that the radical has already been simplified, or it already is in its simplest form. Then the last thing I look to do is, can I divide the numbers by a GCF to fully simplify? The answer is no. So this is my final answer. So that's an example of a quadratic equation where we solve with quadratic formula and it has an imaginary or complex solution. And then last example. In an example like this, if we were to find the solutions to this equation, or the zeros of this equation, I would just solve directly for x. There's nothing stopping me from isolating x. But let's say we want to use the quadratic formula. Set it equal to 0, identify a, b, and c. Remember, b is the term in front of x, or the constant coefficient in front of the linear term. There is no linear term, so b in this case is 0, and c is 25. So I just wanted to show this example to point that out. Now, substitute in -0 plus or minus the square root of 0 squared minus 4 times a times c, all over 2 times a. Negative 0 is just nothing, so we just have plus or minus. Underneath, 0 squared is 0, so we're going to have -4 times 9 times 25. Well, 4 and 25 gets you 100, times 9 gets you -900 in total, over 18. Here's that example where we have a negative under the square root again, so all you have to do is erase the negative and put an I out in front, because negative square roots imply we have an imaginary number there. Then I simplify the radical as we would before. Square root of 900. Before I break it down, I ask myself, is 900 a perfect square? And it is. 30 times 30 gets you 900. So I can replace square root of 900 with 30. People often write the I after the constant, so it would be 30i over 18. Then lastly, I say, can I divide the numbers by GCF to fully simplify? 30 and 18 are both divisible by 6. So 5i over 3. And there's your final answer. So there's an example with a b term that's not there. So I just call it 0. And another example of when I have a negative under the square root and how to handle that. So those are some examples on how to use quadratic formula and the different cases that would pop up in various examples.